discussed with ground wave propagation. As we know, we have three types of propagation mechanism. One is the ground wave propagation, second one is the skyway, and third one is the space wave propagation. Depends on the altitude where we are going to send our signal. So depends on the level of communication where your signal passes through. Based on that, we have just classified into ground wave, phase wave, and skyway propagation. So in the previous session, as I told you, we have discussed the factors influencing ground wave propagation. In this session, we'll start with the skyway propagation. So another skyway propagation. So skyway propagation, from this we can understand our electromagnetic wave from the antenna will be transported over the sky medium, where your signal will get reflected back to the earth. Okay, so there will be transmitting antenna. From the transmitting antenna, your wave will pass through the sky. There it will get reflected back, and it will reach the receiving antenna. This is a simple mechanism that is behind of working in a skyway propagation. So we'll discuss the factors which are influencing the skyway propagation, and we'll understand the concept of how the signals are getting reflected by the atmosphere. That is what we are going to see in this particular session. Especially the skyway propagation is meant for very high frequency range of communication. Very high frequency range of communication will be used for skyway propagation, usually for the applications of broadcasting. Broadcasting application uses very high frequency range in the megahertz and 10 past 8 frequency ranges, which are propagated through skywaves. So skywaves are also called as ionospheric wave, because ionosphere is going to have much impact on skyway propagation, because we are going to use the ions present in the sky to make my signal to propagate to the destination point. So that skyway wave also called as ionospheric wave. And then this propagation of skyway, that is the propagation of ionospheric wave or skyway, propagation of skyway wave revolves around the concept. That is, the mechanism behind the skyway propagation is refraction mechanism. Skyway revolves around the refraction mechanism that is happening in the ionosphere. So we need to understand the layer, that is the space level above the Earth's surface, where much of the ion concentration will be there. I am going to use of the ion concentration to refract your signal, and finally to reflect your signal to get back to the Earth's surface. So where the receiving antenna is located. So that concept is the major mechanism behind your skyway propagation. First of all, we need to understand what is ionosphere, what is actually ions, how it is getting generated in the particular layer, how much concentrated it is. That we are going to study it by visualizing the various levels of ionosphere layer. So next subheading is structural details of ionosphere. First of all, ionosphere is simply the region above Earth. Very simple. This is the space over the Earth, and it is composed of ionized layers. And ionosphere here, it represents the concentration of ionized electron. Ionized electron. I am going to use of this electron for my wave propagation. Above a certain distance from the above Earth surface, where your ionized electron will be concentrated at certain layer. So that kind of that particular layers are here termed as ionosphere, where I am going to utilize the ionic characteristics of my electron to make my wave propagation. So we'll draw the diagram, we'll see the diagram. So from that you can easily understand which layer is concentrated more and which is going to be utilized for different applications. So but here the issue is here the point to be noted is this ionized electron will be maximum. So depends on the atmospheric condition that is happening in the space. So say for example during night session, electron concentration may vary. Similarly, it is not same as when the day is the session for calculating your concentration of electrons in the ionosphere. So it will vary depends on the session where when we are measuring our electron density. We'll see the difference between the ionized electron concentration for both day session and night session. During day, consider this is your Earth surface. This during day. What about your electron density? That we are going to plot it as a layer. So they are termed here. They are given some specification for the particular layer. Depends on the concentration of electrons. So first one is the D layer. First layer is your D layer, which is about 50 to 90 kilometer above the Earth's surface. Okay, and then the second layer that is existing over the D layer is E layer, which is located about which is located about 90 to 140 kilometers from the Earth's surface, where the layers are differentiated according to the electron concentration that is residing in the particular height of the Earth's surface. So depends on that only we are just classifying to different layers of ionosphere. Above this E layer is F1 layer. F1 layer is happening about 150 to 240 kilometers above the Earth's surface, and the final layer is F2 layer, which is located about 250 to 300 kilometers. So this is the various layers above the Earth's surface, where it is classified according to the electron density in that particular layer. From the distance of 50 to 190 kilometer, where you will be having electron density. So depends on the level of ionized electron. It is termed as D layer, E layer, F1 layer, and F2 layer. This is the case where we can differentiate the four layers during the day session. It will not be same when you measure the same electron density during night session. We will see what happens to this layer when it comes to night session. So consider again Earth's surface. This is the electron concentration, that is the ionization layer during the night session. So when you measure it, you are able to differentiate only two layers of ion concentration. So this is the one layer and this one is the second layer. So, so during night session, the F2 and F1 layer will combine together to form a combined F layer. F1 and F2 will combine together to form combined F layer. So, which means during night session, you are not able to differentiate this is F1 layer and this is F2 layer. It happens only for day. During night session, they both combine together to form a single layer of ionized electron. Similarly, D and E layer will combine together to form a single layer during the night session. F2 layer is a daytime mechanism. It exists both day and night. F2 layer exists at both day sessions and night sessions. F1 is a very dense when sunrise sunrise and it vanishes. It is a denser medium during the day session. When it comes to sunset, okay, so during that sunset, this layer's density slowly reduces and it combines with the F2 layer. Sorry, this one is F1 layer. Similarly, E is a daylight phenomena, which means D layer exists only in daylight. Okay, so during daylight only you are able to see the E layer. During night session, D layer will combine with the E layer to form a single layer here, and then this is also a daylight phenomena. Daylight, as you can see, during day only you are able to differentiate E layer and F layer. During the night session, they both combine together because this is a daylight mechanism. It will exist during day session only. During night session, they combine together to form a single layer. Similar to that, F1, F2 will exist. You are able to differentiate during the day session only. Depends on the ion concentration. When it comes to the night session, they combine together. The density will reduce. Because of that, they will club together to form a single layer. So this is a comparison of your ionospheric layers. This happens for during day session, and you are able to see only two layers during the night session. So this is the structure of your ionosphere for two different sessions. Uh, Actually, I have summarized different layer and what are the importance of different layers. So accordingly, they will work to propagate your signal. We'll see the importance of each and every layer. First, we will see the D layer and where it exists and what is the importance of D layer. D layer, as I mentioned the diagram, it exists for about 50 to 90 kilometer from the Earth's surface, and it is a daytime phenomena. What does it mean? It is a daytime phenomena, so that in during night it will not exist uh, alone. It will combine with some other layer to form a existence. It is absent in night. Absent in night. Similarly, the ionization, the maximum electron concentration is low in this particular layer. Ionization is low. Ionization is low means we are not having sufficient amount of electron density to make your wave propagation. That is what it indicates. Ionization is low. So above the Earth surface, the electron density in the D layer is somewhat low compared to all other higher layers. That is what here ionization is low. So because of this, we have less UV penetration. During very low frequency, this particular D layer will act as a huge waveguide. So during, when the operating frequency is about very low, so during the operation, your D layer will act as a waveguide, which means it is like a guided structure through which your wave is getting propagated. So during when you increase the operating frequency from very low frequency to medium frequency, it will give you the absorption of your signal. That is, that D layer will have the property of absorbing whatever the signal that you want to transmit. So when you use a very low frequency, there your signal will get trapped within the D layer to make propagation to the destination point. When it comes to medium frequency of operation, there your signal is getting absorbed within the D layer instead of getting propagated. So that is so because of this reason, this D layer of propagation is it is limited one. So that now we move on to the next layer. E layer. So where E layer exists about a 90 to 140 kilometer, and the ion concentration of E layer is, it is very maximum at 140 kilometer distance, and then it is mostly used for medium distance communication. It is not for very high frequency communication. Medium distance communication applications uses E layer. That is of frequency of about low frequency to high frequency band. So during night session, D and E layers combine together to form a single layer. So actually we have started a skyway propagation. I'll quickly recollect what we have seen in the year. Skyway propagation is based on purely the ionospheric propagation, so that it is also called as ionospheric wave. It is revolving around, that is, it is based on the mechanism of refraction by ionosphere. What is ionosphere? Ionosphere is a uh, layer where your electron density will be maximum. I'm going to use the electron density to make my propagation to refract and get reflected back to the earth. So I just drawn the ionospheric structure. During day session, what about the layer? Similarly, during night session, what happens to the ionospheric layers? And then we have seen what is the functionality and the usage of D layer and E layer. In continuation with that, we are going to see F1 layer functionality and F2 layer. So F1 layer, it exists about 150 to 250 kilometer distance from the Earth surface, above the Earth surface. It happens this this much range of existence for F1 layer during summer season. The same will be about 150 to 300 kilometer coverage of F1 layer during winter season. So the concentration of electrons in the distance of about 150 to 250 or 150 to 300 depends on the monsoon. So depends on that, it will vary the level of concentration. But during that period, either summer or winter, during the entire level, the ion concentration is almost constant. So because of that, you can cleverly use the F1 layer to make your propagation, because the ion concentration is will always be almost constant. And so next one is the F2 layer. F2 layer, it is existing of about 250 to 400 kilometer, and at night session, F1 and F2 combine together to form a single F layer. And then here the issue compared to the D and E layer is, here during night session, this will combine together. The concentration of the ions here, it will be almost constant, because it is, that is, the entire layer will be having uniformly distributed electrons. But for F1 and F2 layer, the variation, that is the distribution of your ionized electron, will be varying one. Because of that, somewhere you will be having a higher density of electron, somewhere you will be having some lower density. It will keep on vary along the entire F1 F2 layer. Sorry, I mentioned it as F1. So F1 is almost constant, but F2 is going to vary. Because of that, what happens? So this F1 is, that is the lower part of the F layer, is going to be constant ion density. Similarly, the top of the F layer will be having varying electron density. Bottom will be the constant electron density. This is a variable in nature. So this particular F layers are used for long distance communication. So actually, so far we have discussed the various layers of ionosphere which are used for various ranges of communication, frequency ranges. In addition to D, E, F1, F2 layers, there are some more layers which are available in the ionosphere. Those are very less significantly used for making communication process. So the other layer that is existing in your ionosphere or sporadic E layer, sporadic E layer. Sporadic E layer. This layer is the result of the natural anomalies that is happening in the atmosphere. So, for example, if a thunderstorm or a thunderstorm is coming, that will create some instant of generation of charges, which is simultaneously that is happening when it occurs. So that is going to give you sporadic E layer. So that is due to the result of anomalous phenomena, and it falls under the category of irregular variation. And it falls under the category of irregular variation because this irregularity will be generated at any random time. So due to that, it will give you a sporadic. It is not a linear generation of your charges. It is a resultant of some irregular random motion that is happening in the ionosphere. So as the name and the generation of this particular layer indicate, it is a random nature. So it is unpredictable because we cannot say when it is going to occur. So that's why this sporadic E layer is the unpredictable one. We are not able to say when this particular layer is going to be generated. So in addition to that, we have some undesirable property due to the sporadic E layer. So the generation of this sporadic layer will cause you some loss of information due to the negative aspects of this sporadic E layer. It will additionally absorb because since the space will is leaky and lost in nature, it will absorb some amount of energy while make propagation. So due to the sporadic E layer, it will cause some additional absorption that will give you reduced amount of signal transmission to the receiving antenna. So and then it will cause you multipath problems, and it will also give you additional delay in your propagation. Additional delay in your propagation. And the final undesirable and the layer which has very less significance is C layer. It happens about 50 to 70 kilometers from the earth surface, that is which is very far below the D layer. The formation of C layer will not cause you, it will not give you any significance of signal transmission, so it is less significant only. This we are not using it for uh, any signal communication. And then we'll see some more definitions regarding the skyway propagation, which are very essential to understand how your wave is getting refracted by the ionosphere to get back to the earth the surface where the receiver is located. So to understand that, we are going to see some basic definitions about the skyway propagation parameter. So on that we are going to see very basic parameter for this. First one is the ray path. Ray path is the first parameter, the name clearly indicates that ray path, which where your ray that is taking the path to reach the ionosphere from the Earth surface, that is from the transmitter to ionosphere, and then get back to the surface at the receiver station. The path it is taking to travel from Earth surface, transmitter to space, space to again Earth surface, that is the receiver side. The path taken by the wave is called ray path. So this simply can be explained as path followed by a path followed by a wave. So this can be pictorially represented as, and there will be a threshold below which only you are able to receive a signal back. So consider you have a transmitter here and you have two receivers here, receiver 1 and receiver 2, located at far away from the transmitting antenna. Now you should transmit your signal from here. It has to go to the ionosphere. There the signal should be refracted to get back to the receiver station. That has to happen. How it is going to happen? That depends on the angle of incidence, where there is a particular angle below which your signal will not be able to travel to the ionosphere. It will fall behind. If you increase your angle of incidence, it will penetrate the particular ionospheric layer and it will go out of the ionospheric layer. So it will not come back to reach the receiver. So because of that, we need to choose the proper angle of incidence by which your signal is able to get back to the Earth surface. So that will be pictorially represented at different angle of incidence of your particular wave. So when you consider a wave is getting generated here, consider this is your ionosphere. If the angle of incidence for the normal line, for the normal, when you calculate the angle of incidence here, so this is phi. If this is angle of incidence, if this is greater than some particular angle called critical angle, we'll see it later. If it is greater than your critical angle, your signal is not able to get uh, refracted by your ionospheric medium. Instead of that, it will get penetrated through the ionospheric layer and it will go out of the site of your communication system, so that your signal will go out. It will not get back. Similarly, when you when you decrease the angle of incidence, your wave will start to come under the ionospheric propagation for refraction. So it is making a angle, say for example phi 5. So then this particular wave also get penetrated to the ionospheric layer. When you further decrease the angle of incidence, there your wave is getting refracted by the ionosphere and it reaches the receiver. The reception of the signal at receiver 1 or 2 depends on the angle of incidence that you are making to the propagation. So it is making an angle, say for example pi 4. Similarly, if you, this is ray 5 and this is ray 3, which is making an angle phi 3. Similarly, so this is ray 2, which is having some quite smaller angle of incidence. Here the signal will be reaching the receiver, and finally when the angle of incidence is far below, which is making angle phi 1, and this is ray 1 and this is ray 2 and this one is ray 4. So as you can see, when you have higher incidence angle to the vertical normal line, so for that signal your signal will not come into the ionospheric layer, it will penetrate through the ionospheric layer and it will go out. Okay, when you take very larger incidence angle, there your signal will not go to the receiver. Instead, it will go further. So the in between three rays, that is ray 2, 3, these three layers will give you the proper reception of signal at an angle phi 2, phi 3, phi 4. These three angles are coming under the range only which signals that are coming within that range can reach the destination point. So here there we have another parameter that we will discuss later, that is called skip distance. So the transmitter to receiver distance, for receiver 1 is skip distance 1. We'll see the definition for skip distance 1, and this one is the transmitter to receiver 2 distance is called skip distance 2. Skip distance is nothing but your signal is able to get refracted by the ionosphere layer to reach the receiver without any disruption. That distance is called as skip distance. Here we need to understand angle phi 6 is always less than phi 5. Similarly, it is always less than phi 4, phi 3, phi 2 and phi 1. Okay. So as you can see, when you increase the angle of incidence to the normal line, so phi 1 is always greater than the other angle which is making incidence on the ionosphere layer. That is what I have written here. Similarly, we need to understand one more parameter called refractive index. We know that the wave's velocity divided by free space velocity. The ratio is called as sorry, this one is actually velocity of light in a free space to the velocity of light in a medium. So usually light velocity, your wave velocity will always be lesser than your light velocity. So this particular parameter will cause some influence on your wave propagation. So here concentration of electrons will be there. That ion concentration will not let you to signal to make propagation by opposing that ion concentration. Only your signal has to pass through. Okay. So whether it is able to do or not, that depends on the refractive index parameter small n. So for achieving the proper communication, we should have n6, n5, n4, n3 and n1 and n1. So this is the typical refractive index value that we should keep to make your propagation. The optimum value of refractive index should fall within the medium range. So here we need to consider a condition where when your operating frequency is greater than your critical frequency, the effect of ionosphere depends on angle of incidence phi naught, which in so this particular condition gives you the basic understanding of how your wave is getting propagated. So we'll have an operating frequency for my propagation. If that particular propagation is operating with a specific frequency which is greater than your critical frequency, so there the ionospheric effect will be influenced by the angle of incidence. Here we can say that, so we have certain amount of ion density in the ionospheric layer. If the angle of incidence is greater than your critical proper angle phi naught, angle of incidence phi naught is the critical value. If it is exceeding that phi naught, your wave will get penetrated and it will go out. Similarly, if the critical angle is less than that of value, your wave will not reach the receiver at a proper distance. So we have to go with the optimum values of the angle of incidence, which will make your signal reception at different receiver position. So to understand this, we need to see another parameter, critical frequency, because based on the critical frequency only you can say whether your wave is going to be propagated or it is getting penetrated. So depends on the parameter critical frequency Fc. So this can be defined as the highest frequency that returns from an ionosphere ionosphere layer at a vertical incidence. Here, critical frequencies are related with the ion density, which is equal to n sub 6 maximum, which refers your critical frequency is directly proportional to square root of maximum electron density in that particular ionospheric layer. If you are making the propagation in a D layer, what about the electron density in that particular D layer? That will be directly proportional to your critical frequency with the square root factor. So here, as you can see, your wave, when you transmit a ray 6, due to the angle of incidence not meeting with the condition, it is getting penetrated out. Okay, so when you reduce the when you change the angle to 5, so still your wave is getting penetrated, it is not coming back. But when the angle of incidence is 5, 4, your wave is able to get back to the Earth surface again. So this is the frequency where you are able to receive, you are able to get back your signal. So this is your highest frequency. This particular race frequency is called as critical frequency FC. So with this we'll stop here. We'll continue with the remaining parameters in the next session. Thank you.
Okay, good morning. Today going to see about DNS. The DNS stands for Domain Name System.